One of the very powerful applications of matrices is using them to solve systems of equations. And in fact, in engineering and other fields, this is how we solve large groups of systems that have many, many variables in them. In this first part, we're just going to use matrices to set up the systems. In the second screencast that's going to follow, we're going to actually use matrices and the matrix inverse to solve those systems of equations. Our world is made up of complex systems of things, whether they're trusses on a bridge, where we're analyzing the forces of those trusses, parts of a circuit, and all the devices that we use, combining their resistors, their capacitors, whether it's modeling storms and all the complex parts of storms, which can be represented by systems, modeling the cells in a body and how they interact, or whether it's monitoring networks and how the parts of a network interact. All of these things are dynamic systems that often behave in a linear way, and we need to find a way to model large systems. That's where matrices come in. This is a system of 3 variables with 3 linear equations, and you can see each of the x's has a different coefficient, the y's have their own coefficients, and the z's have their own coefficients. And there's this right-hand column that represents what each of those linear systems is equal to. And we can represent that with a matrix where the first column represents all the x coefficients, the second column the y coefficients, and the third column the z coefficients. So this can be represented with a 3x3 matrix, and then we have a 1-column 3-row matrix with the variables x, y, and z in them. And then the right-hand column on the other side of the equal sign represents what these linear systems are all equal to. So matrices are very compact ways to store information. These all represent 3-dimensional planes, and the solution to that system of equations, if it does have a solution, represents the intersection of those planes. And you can see visually what each of these is a different plane and how they come together to form the solution. Doesn't always happen, but it does in this case. So let's look at some other practical uses of matrices to represent information. One very common use of matrices is in representing pixels on a screen. Now, this is a simple black and white image with the matrix smiley, and each of these elements in the matrix, it's a very large matrix here, each of these elements, if it's a 1, represents white, and if it's a 0, represents black. So 1 means we're going to make that pixel white, 0 means we're going to make that pixel black. And if you look closely at this matrix, you can actually see the image of smiley. All the image processing that you see, whether it's a video game or photography that's digital photography, all the image processing is done using matrices. So here's a typical kind of mixture problem, and mixture problems are very good applications of matrices. You see them in chemistry all the time. Here's an example from cooking. Let's say we're trying to make a cream mixture with cream and milk that is 14% butterfat. And the cream has 20% butterfat, and the milk has 5% butterfat. And we're trying to find the right mixture of those two things to get a total solution of 10 gallons of cream that is 14% butterfat. So what do we know here? Well, we're mixing the cream and the milk to get a 14% butterfat mixture. Okay? What we're trying to do is come up with the equations that link these two things together. And we got cream and milk, so we got 2 things. We're going to need at least 2 equations to make this work. We also know that the cream is 20% butterfat and the milk is 5% fat. And then something that is often left out in these kind of situations is remember that they have to add together. And they're adding together to get 10 gallons. So the total of the cream and milk is 10 gallons. So let's turn this into a matrix. First of all, I'm going to use C and M to denote the variables. Cream for the amount, C for the amount of cream, M for the amount of milk. And then we're going to put each equation on one line of the matrix and what they're totaling in the right-hand column. So let's put this together. We're going to put the totals on one line, and the amount of cream, 1 times the amount of cream plus 1 times the amount of milk, has to equal 10 total gallons. So that's kind of this bottom row of the matrices here. The top row is going to be the percentage of butterfat that we need in each to get that final mixture of 14. We need 20% of cream, we need 5% of milk to give us 14% total butterfat. So in the end, we have 2 equations, we have 2 unknowns, and that's going to be our setup of the matrices. So the solution to this is going to give us how much cream and milk we need to make that mixture right. And whether it's 2 variables and 2 unknowns or 50 variables and 50 unknowns for a really complex mixture of things, that's how mixture situations work. Speaking of mixtures here, so another type of situation we can have is a mixture of investments. Let's say a friend of yours has investments that are returning annual rates of return of 5%, 7%, and 8%. So we've got 3 investments at 3 different rates of return. We also know she has 3 times as much money invested in the higher rate of return, the 8%, as she does in the 5%. So that's another important fact. And she's got a total of $1,600 invested. And for the year, her interest from those rates of return is $115. So 3 important facts of information here. 3 unknowns, which is the amount she has invested in each of the 3 different types of investments. So we're going to need a 3x3 matrix to represent this. So what do we know? The 3 accounts are at 5, 7, and 8% interest. Let's call them A, B, and C, but you can call them anything you want. We also know that there's 3 times in the amount invested in the C as there is A, it's 5%. And we know the total amount of the investments is $1,600, and their interest is $115. So let's turn that into equations. We know A, B, and C are the 3 accounts. We know that C is equal to 3A. So if C equals 3A, that means that if we move the C to the other side, 3A minus C is equal to 0, and that's going to be another equation. It's probably the trickiest of the 3. And we know that their total must be 1,600. A plus B plus C. And we know the totals of the investments times their individual rates of return has to equal 115 for 1 year. So let's turn that into a matrix. So I chose to put the total first. 1 times A plus 1 times B plus 1 times C has to equal 1,600. The order is not really important. Then the investments times their rate of return is equal to 115. The 5% times A, the 7% times B, and the 8% times C have to equal 115 for the year. And finally, the trickiest of all is that 3A minus C equals 0. So B doesn't have anything to do with this equation, but we know that 3 times A minus 1 times C has to equal 0. The solution of this matrix, the solution of this system of 3 linear equations, is going to give us the amount that she has invested in A, B, and C. So we've looked at how to set up matrices and use them to solve complicated situations that involve systems of information, linear systems of information. We're going to look at how to actually solve them now using matrices.